Hello ladies and gentlemen, thanks for tuning in today to what is the 11th lecture in GGS 300 Quantitative Methods for Spatial Sciences. Today we're going to be focusing on categorical difference tests. So where are we at within the course at the moment? Well, I've set a number of tests for you, unmarked tests, which essentially are going to be preparing you for the midterm. And I think most of you now have completed those initial tests which have been set. There might be a couple more which I'll need you to complete. And then at the end of this week, we're going to have the midterm exam, which hopefully you're all going to have time to revise for. So there won't be a laboratory session this week. There's just going to be time for you to basically go over the materials from this unit of the course, so this part that's focused on inferential statistics. And hopefully then you'll be able to do some prep to get you in a good state in order to do really, really well on the midterm that's coming up. Reach out to me if you've got any queries. Again, I'm enjoying the engagement that I'm having with some of you via email or Zoom, so please do reach out to me if you want to get in contact, have a chat about the course, let me know how you're feeling. I think that that's a good dialogue to have, and I think that those people that have reached out and spoken to me hopefully have got something out of it, and hopefully you've got a better understanding of the course as a result. So if you're sat there being hesitant, don't be, and please just reach out to me if you've got any queries or questions. So today I'm going to be focusing on this introduction to categorical difference tests, and we're going to be going over the book. It's chapter 12, and we're going to be covering about 3 different tests essentially, which will be providing the theory and some examples in order for you to carry out these tests on your own. As I say, there's not going to be a lab this week, so we're not going to be working through any R-code examples on these categorical difference tests, but obviously if you need to do that for your dissertation or some other part of your work, then you have the baseline materials, and you can always reach out to me or reach out to the materials to look at what you need to do if you need further understanding. So where are we? Well, we covered in the first unit of the course the basic descriptive statistics, which covered this left-hand part of this spatial scientific process diagram, which I've presented to you already this term. And the last unit, so this is the last session for Unit 2, has then introduced inferential statistics, so essentially how we collect and prepare data, how we test formal hypotheses that we make and then evaluate them based on the statistical results that we obtain. And hopefully once you've got that information, you're either able to return back to the theory or the model that you're developing, or you're able to make judgments about the world, and hopefully that will inform your decision making, make the world a better place. That's what we're here to do. So if that's the scientific process, then you'll remember that this is a flowchart for those commonly used statistical tests. And I've used this now in the last couple of lectures. So essentially we've focused mainly over the last couple of lectures on continuous data. We were down here focusing on the variety of different treatment groups. So we covered, if you have 2 groups, we covered parametric and non-parametric tests, which include the t-test and the Mann-Whitney U and Wilcoxon-Rank sums test. And then if you had more than 2 groups, then you'd be able to use ANOVA, as we did last week, so the analysis of variance, and also the critical Wallace test, for example, if you have non-parametric data. So where are we going? Well, today we're all the way back at the top here, and we're focusing on categorical data, and we're going to be focusing on the chi-squared test, for example. So that's a bit of background for where we've come from. Now let's get into the nitty-gritty and look at what we're covering today. So we're going to be focusing on goodness of fit tests. And I know what you're saying. You're going to say, haven't we covered enough tests already? And I really appreciate that thought. I feel like in this particular course, what we've done is we've done a very quick tour across all of the different tests that are available to you. So you remember in the flowchart, it looks quite daunting, all those different tests. And what we've done is we've dipped into each one and we provided theoretical ways to calculate the stats and then empirical ways to carry out the tests. And that's good, but we haven't gone that deep into each of them. I mean, maybe we've done 1 or 2 tests for each. Ultimately, people spend their entire careers working on just 1 or 2 of these individual tests. So you could go into a lot more depth, and I think that's really the point of what we've done here. We've gone across the landscape in a little bit of depth, but we've given you good breadth of understanding of all of the statistical tests. And if you need to go off and do further research, using one of those particular tests, then you can kind of do a deep dive into it to get a better understanding of the more nuanced issues associated with each approach. So what have we done? Well, essentially we focused firstly on one sample test, so comparing a single sample statistic to a corresponding population parameter. Then we focused on two sample tests, so we evaluated independent samples, and then we also looked at paired dependent samples, so matched pairs difference tests. And then more recently we've done the ANOVA approach, so looking at 3 or more samples. But most of these, well, all of these obviously are continuous. They could be ordinal, if you had to downgrade the data to use a non-parametric approach for one of these. But generally, we haven't addressed categorical data within these particular approaches. So that's what we're going to be doing today, focusing on nominal data approaches. And it is possible using goodness of fit tests. And we've got 3 of them. We've got the 3 that we're going to be covering today: the chi-squared goodness of fit test, the Kolmogorov-Smirnov goodness of fit test. So this is one particular approach. There's also the Shapiro-Wilk test that we'll cover very briefly. And then there's contingency analysis, which we'll go into. So the 3 different approaches, both the chi-squared goodness of fits test and the contingency analysis approach, use the chi-squared distribution and are calculated in a similar way. The Kolmogorov-Smirnov goodness of fit test is for ordinal data. It uses a slightly different approach, so it's using the cumulative distribution, and it's comparing a data sample that you've collected against a theoretical cumulative distribution to look at whether your data are normally distributed or not. So in the goodness of fit tests, as I said briefly, the point is we want to take a set of observed data that maybe we went out and collected. So we went and did a sampling exercise, and maybe we ended up with a set of data for all these different categories. We then want to understand if that data that we collected across those categories is similar or significantly different to what we would just expect from a frequency distribution, which is based on an element of randomness that isn't potentially significant. So there is always that element of randomness as a result of there's always an element of variation as a result of the randomness in our approach from sampling. But the question is it significantly different? So do we, as a consequence, need to make a decision associated with how we approach the analysis of that data, whether it's parametric or non-parametric as a consequence? So how much does the distribution deviate from what is expected? And there's 3 different ways that I want us to think about this, and we're going to cover these 3 different approaches in the tests. So the deviation can be whether the data are uniformly distributed, whether they are proportionally distributed, or whether they're normally distributed. And those tests that we'll be covering will focus on each one of these aspects. So whether we're using the chi-squared statistic or the Kolmogorov-Smirnov difference-based approach. So how do we calculate chi-squared? Well, what we're trying to do in this test is to compare observed frequencies with expected frequencies that we would expect to occur at random. And there are certain assumptions that we need to meet in order to reliably use this test. So the requirements here are that we have a single random sample, that the variables are nominal or ordinal with frequency counts. So that could be data that we've collected in that particular way through a survey-based approach, or if you or maybe you had to downgrade data to being ordinal. And generally, these are kind of requirements up here for how we carry out the test. But then these bottom 2 here relate more to preventing over biasing of the results, and then that's essentially that you need to make sure that you have no frequency in any category that has less than 2 observations, and you need to make sure that 1/5 of the expected frequency counts, more than 1/5 of the expected frequency counts, are above 5. So this is basically just trying to avoid the test results being biased as a consequence of maybe you not having enough data points across the different categories that you're interested in testing. So we need to make sure that we meet these requirements, and if you're carrying out a test as part of your dissertation research, for example, then you will need to make sure that you state these assumptions at the beginning and then state in the method how you are going to make sure that the data that you collect meets these requirements in order for the results to be reliable, essentially. So what are the hypotheses going to be? Well, the null hypothesis essentially is that the population fits the expected frequency distribution and that the data that you've collected are not significantly different. And then the alternative hypothesis is that the data essentially are significantly different and the population does not fit the expected frequency distribution. The chi-squared is the test statistic, as we've got here, and then we need to calculate the chi-squared value. So firstly, what we need to do is need to get the number of categories that we have, so this k value here is the number of nominal ordinal categories. And then essentially we need to make sure that we get the observed actual frequency count for each category, which is OI. Then we need to calculate the expected frequency count, which is EI, and that provides us, when we subtract EI from OI and square it, provides us with the numerator. And then we have the denominator also being EI. So we'll work out how to calculate that later. This is just the high-level math for how you actually get the chi-squared statistic. And we will look at how you calculate that now. So essentially, we're looking at whether the observed values are close to expected, or whether, sorry, if all the observed values are close to expected, the differences essentially are small and chi-squared will be small, in which case we would fail to reject the null hypothesis. So the opposite to that obviously is that if at least one of the observed values that we get is large, then the chi-squared value is going to be large, and therefore, depending on what the value is that we obtain, we're more likely to reject the null hypothesis, because it would be potentially more likely that you have a significantly different data from the population. So what does that mean? Obviously all that's quite high level. Let's work through an example now. And there is an example which we replicate here in the book, so let me just find the page for you. So it's page 189 in chapter 12. I'll just add that into the slides for you. Okay, so we have a random sample of 100 students from 5 different schools, and we want to assess whether the distribution of students that we have that are above the national median scores is uniform between the schools. So we look at how students are performing. We're interested in whether the proportion of students performing above the national median is the same across all of these schools, or perhaps, is there a difference? And if there is, then what that means is that some schools are performing better or worse than others, and that may mean that we have to design a program to intervene in order to ensure that maybe good schools can continue to do what they do, but the schools that are underperforming can be brought up to meet that national median level, or broadly that national median level. Okay, so we have a set of observed number of students above the national median score here by school. So we have these 5 different schools, so Muir, Pinchot, Carson, Hardin, Leopold, and we have all of these different student counts here, so 42, 45, 51, 47, 60. When you add all of them up, you get 245, okay? And we want to get the chi-squared statistic here. So what we first need to do is get the k value. Well, that's 5 different categories that we've got. So k is 5, as you can see just here. We need to get the EI value as well, the expected outcome. And the way that we do that is we sum all of the observations that we have. So here it's 245 students overall. And so that's the numerator, and we need to divide it by the k value, the number of categories we've got, which is 5. And therefore we get an expected number of students for each school of 49 that we would expect to be above the median national level. Essentially, when we then take the data that we have here for the actual observations and the expected number, the expected frequency of students, we're able to run through this calculation here. So what we're doing is we're taking the 42 for school number 1 and subtracting it from the expected frequency 49, dividing it by 49, and getting the result of this. And we're going along, you'll see that the 45 students here is in the second equation, 51 here is in the third equation, and we need to sum all of these until we get the chi-squared value here, which, the chi-squared isn't that large, it's 2.007. So at 4 degrees of freedom, we get a p-value of about 0.734. So if your p-value is at 1, that means that data are basically identical to the expected frequency. If your p-value is 0, then it's going to be highly significantly different than what you would expect to occur at random. As a result here, 0.734, it's not below the 0.05 significance level that we've been using in the previous examples. So we do not have enough evidence here to reject the null hypothesis, essentially. So it looks as if from this data here, these data essentially have been collected in a way that means that they are broadly similar to the distribution that you would expect. So quite uniformly distributed. So what this means essentially is that you would expect that the variation occurring between schools in terms of their performance is just random variation. There doesn't seem to be a significant difference going on here, where maybe you have some schools performing better and some schools performing much worse. So that could feed through into the decision which you make for how you design your future strategic plan for improving schools and how you allocate resources. So maybe as a consequence you allocate your resources evenly across all the schools because they all seem to be performing in a fairly similar way for the 5 that we've looked here. So let's move on now to the second test which we're going to cover, which is the Kolmogorov-Smirnov goodness of fit test. So the difference here is that we're using ordinal data to judge if a distribution fits some frequency distribution. And we're able to use any type of frequency distribution, but often the normal distribution is used. The question here is, does the data set resemble a normal distribution? And this was one of the first tests which I carried out when I was your age and I was working on undergraduate statistical coursework, essentially. And my point was that I had to go out and collect some data and then carry out a bunch of tests on that data. And my worry was, oh well, is it normally distributed? Because whenever you go out and you do actual sampling, you're probably going to get some quite oddly distributed data at times, and that means that you might want to run a test like this because then it's going to tell you actually this isn't significantly different from what just occurred at random, and therefore you would be safe to use a parametric approach. Or if it was significantly different from what you would expect to occur at random, then you would use a non-parametric approach, and you've got a nice test to demonstrate to your lecturer that essentially you'd thought about this in advance, and then you're able to demonstrate that your data is significantly different, and therefore it justifies using a non-parametric approach, which sometimes might be less statistically powerful than using a parametric-based approach. Okay, so that's what we're looking for here. Does the data that we've got in general resemble a normal distribution or not? And we use this test to see if the normality assumption is valid for parametric-based approaches. So what do we do? Well, I mentioned before that we use the cumulative relative frequency. So just bear with me on this, I'll show you what that means. Essentially, this compares your sample data to the perfect normal distribution to see if they match. And if the distribution is not significantly different, then we'd use a parametric test. So if it's not significantly different, we wouldn't have enough evidence to reject the null hypothesis. And the null hypothesis here is that the distribution is not significantly different from the normal one. Whereas in the alternative, the distribution is significantly different. If the distribution is significantly different, then we would use a, non-parametric test. Okay, so imagine that this is the data that you've collected, and this is your distribution you've got over here. that you've collected randomly, essentially what you do is you convert it to a cumulative data pattern over here. So I'm now just going to give you a quick example. I couldn't remember if we had been over a cumulative distribution example before, but let's just assume that you have January, Feb, March, April, right, so let's assume that this is money that you're putting into a bank account. So let's say on the first month in January you put $5 in the bank account, and let's just say for sake of ease that you put $5 per month in your bank account. The cumulative bank balance as a result over time essentially is as follows. So what you need to do at each stage, once you've got your sequence of data, is you basically need to add the new data point. So here you per month amount, and you add it to what the existing balance is. So assume that in February we've got $10 in our bank account because we had 5 from January and we put another 5 in. So by April we have $20 overall in the bank account because we had 15 in March and we put another $5 in. Okay, so that's just an example of how you get the cumulative frequency or the cumulative balance. So that's essentially what you're doing here. You're taking all of those different ordinal buckets and you're creating the cumulative frequency out of them, and then basically this test takes what would expect to happen using the normal distribution and then what your data has done, and then it would look at whether there was a significant difference there. Okay, so I don't want to get too bogged down in this. Let's have a look at what the test is doing overall. What we want to do is compare random sample frequency counts of a single variable with expected counts. Okay, so you have assumptions that you need to meet, so it needs to be a single random sample. The population needs to assume to be continuously distributed, and the variable that you would expect is ordinal. So essentially, that could be downgraded interval ratio data. So if you were to use this with continuous data, then you would have to convert it into your ordered categories. So what are the hypotheses? Well, essentially, your null hypothesis is that the population which the sample has been drawn from fits the expected frequency distribution, so there's no difference between the observed data that you collected and what you would just expect to occur at random. Whereas with the alternative hypothesis, essentially the population does not fit the expected frequency distribution. So there is significant difference between what you collected, the observed sample data, and the expected sample data. The difference here is that we're using test statistic D, so D is the maximum absolute difference between what you observe and the expected cumulative relative frequencies. And over here we have the cumulative relative frequencies for observed X, and we have the cumulative relative frequencies for expected X. So this is how you essentially calculate the D value. The problem is that it's actually quite hard to calculate the Kolmogorov-Smirnov test in reality. So basically, to do it manually, if that's what you wanted to do, then basically you would have to convert all of your rank data into Z-scores. You would then need to calculate the cumulative normal values and the cumulative relative frequencies just here. And then you would need to compare with the cumulative relative frequencies expected with the normal distribution. Okay, so it's quite a few different steps. The key point is that what you're looking for is the maximum absolute difference between the observed frequencies and the expected frequencies. So this is much like the previous test that we covered with chi-squared. If your test statistic comes out as a small value, then basically you will have a small difference, and then you're more likely to not have enough evidence to reject the null hypothesis. Whereas if you have a large test statistic, you'll have a large difference, and then you're more likely to have enough evidence to reject the null hypothesis and say that, you know, this sample is significantly different from what we would just normally expect to occur. Okay, and yeah, this is complicated to calculate. There is a special table of d-values that you're able to assess in order to understand it. But the key point is that essentially we're not going to be running a Kolmogorov-Smirnov test here. I just want to make you aware of it. If you did want to run one, then I would very much advise you to use the Shapiro-Wilk test to test for the normality of the data, which you're able to do in R relatively easily. So if you need to use it, you can use the Shapiro.test, open bracket, x, close bracket, a based approach. So this is a function name, and you can just put that into R, and you can look at the help menu if you're interested in understanding more about that. But it's exactly the same in terms of the approach. So basically the distribution, the null hypothesis is that the distribution is not different, whereas the alternative hypothesis is that the distribution is different from normal, and therefore if you're using that to inform your statistical test approach, you would use a non-parametric based approach. Okay, so the Shapiro-Wilk does produce a W statistic, and there are some slight differences here. So much like with Kolmogorov-Smirnov, if you end up with a small statistic at the end, then you should reject the null hypothesis, as your data are significantly different from the normal distribution. Hence, you can't use the parametric tests. Yeah, there are some issues with sample size as well that you need to be aware of. So essentially, as the sample size increases, it's more likely that you will find a significant finding. So you need to be more rigorous with the p-value potentially if you've got a large sample. So here, it's normally recommended that you have a sample below 50 for this type of approach. Okay, so that's what you want to do if you need to take a look at how you run that test in R. So let's move on now. So we've covered chi-squared, we've covered the Kolmogorov-Smirnov test assessing normality. So we looked at uniform data in the first instance, and we looked at normality in the second instance. And now we're moving on to contingency analysis. So two categorical variables. So essentially, before we compared an actual observed frequency distribution against an expected frequency distribution. So this expected frequency distribution is the theoretical distribution that we would expect to occur just based on randomness, essentially. And we're comparing if the data sample that we collected either is not significantly different or significantly different from the theoretical distribution. Okay. So the question is, well, actually, what if we want to test cross frequencies for two different variables? So before we were just focusing on a single variable against a theoretical distribution. Here we're interested in comparing two actual data distributions that we collected. So the aim is to see if they are independent, so occurring separately, or if they're actually related, so not independent. So contingency analysis. Essentially, it's a logical extension of the goodness of fit approach that we used previously for a single variable, and it evaluates an entire contingency table as a single entity. So I'm going to cover contingency tables on the next slide, but for now, just accept that it considers the whole thing as a single unit. The contingency table, as I will show you, is essentially cross-tabulated frequency counts across the two variables that we're interested in. And that determines if there are significantly large enough differences between the expected and observed outcomes. And I think the key point as well is that these need to be absolute frequencies, so raw numbers, not proportions. So what's a contingency table? Well, there's lots of different names for it. It depends what you're doing. In classical statistics, it's also called a cross-tabulation. In machine learning, they also have confusion matrices, error matrices. But the point is that this basically just shows your frequency counts when you cross-tabulate across two different variables. So imagine that we have this simple 2x2 grid here, and we've got variable x, which can either be a 1 or a 0, and variable y that can either be a 1 or a 0. And essentially, if your variable x outcome was 1, and then your variable y outcome was 1, and you had 10 participants, which had that same answer from both variables, then you would put a 10 in the A cell just here. And actually, I think that I prefer the name cross-tabulation, as I've just put this little note down here, because that gives you the best kind of indication as to what you're doing when you're creating these contingency tables. Because, you know, cross-tabulate, I think it's easier, it's more illustrative of what you're actually doing when you're creating these types of tables. So this is essential, basically, in order for us to actually calculate the test. So what are we doing? Well, we're comparing the observed frequency counts that we collected for two different variables to see whether they're independent or not independent. The requirements essentially are that you have a single random sample and that the variables that you're going to be working with essentially are nominal or ordinal with frequency counts. And again, you must make sure that the categories that you use aren't underrepresented potentially overall. So you can't have frequencies less than 2. You would either need to go out and sample more or think again about the test that you're using if that was the case. And you can't have less than 1/5 of the expected frequency counts being less than 5 essentially. Okay, so what's the different hypotheses for this particular approach? Well, the null hypothesis essentially is that the variables are statistically independent, so there's no relationship. They are not correlated in any way, for example. Whereas in contrast, the alternative hypothesis is that the variables are not statistically independent, so there is some level of dependence between the variables. And when I talk about whether the errors are correlated, actually we do have a session on correlation coming up in the third part of the course. So I think that that'll be a good time for us to go over what I mean when I talk about the errors being correlated like this. But it's important when you start to do things like regression analysis, which is really quite a strong tool that you can develop towards after you've covered essentially the more basic sample testing that we're doing in this part of the course, so the second unit. So how do we calculate that chi-squared statistic? Well, essentially what we need to do is we need to get the total number of rows, so that's R. We need to get the total number of columns, which is K, just here. And then we need to get the observed frequency counts for the ith row and the jth column. So what do we mean when we say the ith row? Well, just remember that the I is representing a number. So that could be the first column, the second column, the third column, so on and so forth. And we just use that algebraic expression I basically to represent the fact that you can have a table with as many samples in, as many observations in as you like, basically. And this just represents the general formula, so the general relationship as a formula, which means that we don't have to be specific about what we're doing. And actually this is the standard notation that we use to represent matrices. So I represents the row number and J represents the column. So essentially here we're talking about the ith row, so that just depends on the I ith row, and the jth column, so the particular column that you're using. So apologies for having to explain that. This is just the way that statisticians talk, and I know it's complicated when you first start using these tests, so you just need to just hang in there, and hopefully by the end this will be clear to you, and you'll have the basic statistical foundation in which to carry on and go and do fantastic things. So that's how we get the OIJ, the observed frequency count value, and then we want to get the same for the expected frequency count, which we do by calculating over here. So it's the sum of all of the observed frequency counts multiplied by the sum of all the observed column counts. So sorry, this is the sum of the rows and the sum of the columns. It gives you this numerator, and divide it by the total observations, and that gives you the expected number, the expected frequency, so the EIJ for that particular column and row combination. And then we can use that here to get the numerator once we've squared the result of this, and then we can divide it again by the expected frequency count. So that's complicated. It's a long-winded way for me to explain those different metrics to you, but it's obviously better for me to show you in reality. So hopefully that's reasonably clear. You do have the example in the book if you want to look over how to calculate that. So contingency analysis, let's develop a set of tables and let's actually carry out those calculations. So let's just hypothetically pretend that we decided to poll a group of GGS quant methods students by major, and we asked how much you actually liked the quantitative courses that you were taking. So we have two different variables here. We have the particular major, and then we have the degree to which you actually liked the quantitative courses. So imagine that this is our observed frequencies. So we have along the columns here, we have your responses to whether you liked quantitative courses. So yes, a lot. Yeah, it's okay. And then no, not at all. We didn't like quantitative courses over here in this column. And then basically we have the major here. So whether it's a BA geography, BS geography, or something else. And then what we have are the row totals. So this 15 here is the summation of 7 plus 4 equals 11, 11 plus 4 equals 15. So that's how we got this row column here, this row total, sorry, this row total. And then how we also get the column total, which is at the bottom here. So you see this 17 is the 7 plus 5, which is 12, 12 plus 5 equals 17. So that's how we get the column totals here. And this is going to be important for then how we calculate the chi-squared statistic. And we're able to basically get the expected frequency now that we basically have those column totals. So you remember down here, the expected frequency required the sum of the frequency counts across the rows and the sum of the observed frequency counts across the columns and the total number of observations. So when we run through that and we've got the n for the total number of observations and the column and the row counts, we're able to produce these expected frequency counts just here on the bottom. And then once we've got that, we're able to use, so you see the observed values here and E for the expected values here, we're able to calculate that coefficient for each one of the responses. So depending on whether you actually liked the quantitative courses, whether you were a bit ambivalent, you said it was okay, or whether you said it was very bad, very bad. Over here, and then also on the rows, depending on which major you were taking. All right, and then when we get that, so that's the O minus E squared divided by E. So that's the value that you get. Remember that we need to sum basically. So all we have on that right-hand table right now is just these values here. What we don't have are the summed values. So basically, to get the chi-squared, we need to basically sum all the way across the rows and all the way across the columns. And then when you do that, you end up with the chi-squared statistic of 2.763. Okay. And when we actually then we compare that value against the distribution, so the quantile, we can get a p-value of 0.598. So essentially that is not strong enough to provide you with some sort of confidence that the results haven't just occurred by random. So as a consequence, we fail to reject the null hypothesis. So that p-value there, it's nowhere near the standard statistical level that we would expect of 0.05. So there's a good chance that these results just occurred at random, and therefore we don't have strong enough evidence to basically to reject the null hypothesis and accept the alternative hypothesis that there's some sort of dependence between these variables. So these variables essentially are independent based on this particular approach. Okay. So that's bringing to a close the second unit of the course. We have the midterm this week, so you'll be hearing from me. Please do reach out if you have any further questions about that. This midterm will inevitably end up being harder because it's been harder content. So I don't want to I don't want to um, make you be complacent about the test that's coming up. I want you to spend that extra time, please, that you won't be spending doing the lab work, actually preparing for this test, so that you'll be in a strong position to do really, really well on the rest of the course material. Okay, great. Thanks a lot for tuning in. It was good to see you again, and I'll see you all soon. Thank you.